Rotational Kinematics. As always, if you enjoy this content, be sure to like and subscribe. So rotational kinematics is exactly what it sounds like. It's motion, but this time it's spinning. So when we're going to deal with problems like this, it's essentially all the same stuff we've already done in terms of x equals v naught t plus 1/2 at squared. All of that, except now it's rotating. So there's two different ways we can look at this rotation. We can look at the tangential velocity. And what tangential velocity is the velocity of a point on the rim, or it could be a point anywhere along this disk. So let's say we have this disk is spinning like this, and the dotted line represents its axis of rotation. Well, if we say that this point moves a certain distance over to here, then it's carving out this sort of section of pi, and that distance of that outside edge of this little pi slice, we could call that x. And the time that it takes to travel that distance would be t. So we have x divided by t, and that would be our average velocity, or technically speed, because the velocity is changing. But there's another way that we can look at this. Let's say this disk is rotating in this direction, and we have our little slice of pi here. Then we could say that it carves out a certain amount of radians in a given amount of time. So whereas this would be x over t, this would be theta over t. And this we call the velocity, and it would be average, and this we call the angular velocity, and it would be the average. So one thing that we have to be careful about here is that the velocity that is tangential is only at a given point at a radius r. So in other words, this velocity or speed at this point would be much faster way out at the edge than would be a point that's carving out this section right here. But when we're dealing with angular velocity, that's going to be different, because the angular velocity of a point out here, that's the same amount of radians that are carved out as a position in here. So here, the tangential velocity is dependent on radius, whereas angular velocity is not. So what is our formula here? We're going to say that V average is equal to delta x over delta t, and our units would be meters per second. So that's going to be tangential. Angular velocity, we use the lowercase omega, and that's going to be average in this case. And we use theta as our position change over time. And because this is an amount of radians, the unit becomes radians per second instead of meters per second. And if we want to know the instantaneous version of that, well, then we just take the first derivative. So the instantaneous tangential velocity is going to be dx dt, and the instantaneous angular velocity inst, would be d theta dt. Let's go ahead and solve for some different things in here, like the tangential velocity and the angular velocity, for a disk that's spinning. Okay, so this is a disk. It's spinning around like that. It has a radius of 2 meters, and it takes 10 seconds to go around and make one full revolution. Now, we know that one full revolution is going to be 2 pi radians, so that would be our theta. But the first question says, find the tangential velocity at 1 meter. And then we're going to do this again at 2 meters. So 1 meter would be here. So we're looking for the average speed of a point that's moving around 1 meter in a circle. So to do that, we would just say V average is equal to x over t. So V average would equal one full circle would be 2 pi r, the circumference, divided by the time. And that would be equal to 2 pi times 1 meter over 10 seconds. And that would give us a tangential velocity of 0.63 meters per second. So pretty straightforward, pretty basic. So what happens when we go to a further radius? We go out to 2 meters. Well, it's the same problem. It's x over t is equal to 2 pi r. That's our circumference. The time's the same, but the radius is different. So now we're at 2 meters in 10 seconds. So this tangential velocity is going to be 1.3 meters per second, which is going to be double. We've doubled the radius. It's a direct relationship, so the tangential velocity doubles. Well, what's it going to be in terms of angular velocity? Well, angular velocity is going to be the change in the angular displacement, which is theta, divided by time. So that's going to be how many radians in one lap, one revolution? Well, that's 2 pi radians divided by 10 seconds. So that comes out to, an angular velocity of 0.63 radians per second. Again, very basic. But there's an important formula that can help us to move between angular and tangential. And that formula, I call it rho-mega. V equals rho-mega. So our tangential velocity at a point is going to equal the radius times the angular velocity. So we can see that our V tangential equals rho-mega, r times omega. And if we put this in here, we have 1 meter times 0.63 radians per second, and that's going to give us V equals 0.63 meters per second, and that's what we had before. I'm just showing you how this works. So we can also do it at 2 meters. So V is equal to 2 meters. We know the angular velocity is 0.63 radians per second, and that gives us a tangential velocity. I'll put that tangential, equal to 1.3 meters per second. Okay, so that handles situations where a disk is spinning at a constant velocity or constant angular velocity. But what happens if the disk starts to spin faster and faster, or it starts to slow down its rate of spinning? Now, we got to be careful not to confuse this with centripetal acceleration. Centripetal acceleration is v squared over r, and that's the acceleration due to the change in position of a point on the rim. So in that particular situation, when we deal with centripetal acceleration, we have a circle. That's where that position would have gone, and then it moves into this. So we're not dealing with that. So we're not dealing with centripetal acceleration. We're dealing with how a disk starts to spin faster and faster or slower and slower. And we'll get into what causes that later. So for the basics, we have A is equal to delta V over delta t. So we know that's acceleration, but that's also average acceleration. We're not dealing with a changing acceleration. So what would the angular acceleration version of this be? Well, we use the Greek letter alpha for angular acceleration, and that would be the change in what? Well, this is the change in tangential velocity, so this would be the change in angular velocity, and again, with respect to time. So if we wanted to find the instantaneous velocity, that would just be the first derivative, dv dt, and for alpha, instantaneous, that would be d omega dt. Now, we know from before that we could also look at that as the second derivative of position. So therefore, we can also look at this as alpha inst as the second derivative of the angular displacement, theta, with respect to the second derivative of time. So let's just write something down here in terms of direction, okay? If omega is positive, now we get to choose what that is. We could say clockwise spinning is positive, and alpha comes out positive. Well, what does that mean if alpha is in the same direction as omega? Well, this is the same idea as when we had a block which has a velocity to the right and an acceleration to the right. They're in the same direction, so they speed up. So what happens when the angular velocity and the angular acceleration are the same? Well, then we have an increase in angular velocity. And therefore it makes sense that if omega was positive and alpha was opposite of this, negative, then omega would decrease. So the main idea here is when omega and alpha are opposite, it slows down, and when alpha and omega are in the same direction, they speed up. So let's go ahead and take this formula that we know from before, Vf equals V naught plus At. What would the angular version of this formula be? Well, that's, in this case, tangential velocity. We could say that that would be angular velocity. And so that would be angular velocity initial, and this would become alpha, and that would be t. So this is the kinematics formula for angular velocity. But we know that omega final we could write as d theta dt. And then we could set that equal to, if we're doing instantaneous, the initial velocity plus alpha t. And if we integrate that, we integrate d theta and bring our dt to the other side, we have omega initial plus alpha t dt, and that's all of that. Then we can take the integral of d theta, and that's theta, so that would be theta final. And that would be equal to the integral of omega initial dt would become omega t, plus, and then take the integral of alpha t with respect to time, so that would be 1/2 alpha t squared. And then we have our constant, and our constant would be our initial position. But we can subtract this over and just say that that's equal to delta theta is equal to omega t plus 1/2 alpha t squared. So we did an integration to get a new formula, the rotational version of this kinematics formula that we've seen before. So let's go over this all together at once. We know that we have, for linear formulas, we have V final minus V initial plus AT. So therefore, the angular version of that would be omega final equals omega initial plus alpha t. And we know that we have x final equals x initial plus v naught t plus 1/2 at squared. Well, what's the angular version of that formula? That would be theta final equals theta initial plus omega naught t plus 1/2 alpha t squared. And then we can predict what this formula would be. Vf squared equals v naught squared plus 2a delta x. What would that be in angular terms? Omega final squared equals omega initial squared plus 2 alpha delta theta. So we can use these three formulas to be able to solve any angular kinematics problem. In other words, if we have a disk that's spinning and it's angularly accelerating, it's spinning faster and faster, we can find out how fast it's spinning sometime later. And we can use these different formulas to solve different problems depending on what we're given. So there's two other formulas, though, that are necessary because we have linear terms, and sometimes we want to convert between these two. So we've already seen the first one. The first one is what I call ρ. V tangential equals r times omega. Well, there's another one. There's A tangential is equal to r times alpha, which I call ρ as a way to remember that. So we can use these formulas with these conversions to solve any kinematics equations. And the best way for me to show you how to do this is to solve a bunch of problems. And I'll do some problems that use each one of these formulas and these as well so that you can get a hang of doing it. But basically it's the same thing as what we've already done before. Let's just review the units here. We have angular displacement. Angular displacement is theta. That's measured in radians. We have angular velocity, which is omega, measured in radians per second. And we have angular acceleration, which is alpha, measured in radians per second squared. And that's everything we need to know to be able to solve these problems. How did we solve kinematics problems when we were doing them a couple months ago when we started all of this? Well, what we did was we read the problem and then we wrote down the stuff that we know and what we're looking for, and then we chose a formula to solve. So let's do the same thing here. We have a CD of radius 0.06 meters. It starts from rest, so it's not moving. And then this disk accelerates uniformly to 52.5 radians per second. So what is that piece of information? That's our angular velocity. Radians per second tells us that. And it does this in 5.5 seconds. Find the angular acceleration. So let's see, what do we know? Well, we know the angular initial velocity is 0 because it starts at rest. And we know that it speeds up to 52.5 radians per second. That's how fast it's going when at 5.5 seconds. And they want to know the angular acceleration. We're looking for alpha. So the easiest formula to do this with would just be omega final equals omega initial plus alpha t. So we put in our numbers, 52.5 equals, this drops out to 0 because it started at rest, equals alpha times 5.5. So our alpha comes out to 9.5, and that's radians per second squared. The second question says, find the angular displacement. So to do the angular displacement, we're looking now for delta theta. So since we have the angular acceleration, we can do delta theta equals omega t plus 1/2 alpha t squared. We know the initial angular velocity is 0, so that drops out to 0. And we have 1/2 our new alpha, which is 9.5, times our 5.5 squared. And when you do that, you end up with 144 what? Radians, because that is an angular displacement. And then it says, how far does a point on the rim travel? Well, we know the formula S equals r theta. That's the formula for arc length, in case you've forgotten that. So if we want to know how far it's gone, all we have to do is multiply the radius, 0.06, times the angular displacement, 144 radians. And that gives us a number of 8.64 meters. Okay, so in this one it says we have an angular position of a point on the wheel that can be described by theta equals 5 plus 10t plus 2t squared radians. And they want us to find the angular position, the speed, and the acceleration at these different times. So if they're giving us this theta with our angular position, all we have to do is put the numbers in. So that would be 5 plus 10t plus 2t squared. So put in 0 for these, and theta just comes out to 5 radians. If we put in 3 seconds here, and we square 3 times 2, and 3 times 10 is 30 plus 5, then at 3 seconds we get 53 radians. But it gets a little bit more tricky when we're solving for the speed. Because what is the speed? Well, the speed is d theta dt. In other words, it's the first derivative. So what we need is the first derivative of this formula. Well, the 5 will go away, the 10t becomes 10, and the 2t squared becomes 4t. So we have 10 plus 4t. Put in 0, so the angular velocity at 0 seconds would be 10 radians per second. And at 3 seconds, that would just be 10 plus 4 times 3. So that would be 22 radians per second for the angular velocity. And then it says, what's the acceleration? Well, the acceleration would be the first derivative of angular velocity. And that would go to 0, that would just become 4. So what does that tell us? There's no time involved. In other words, the angular acceleration is constant. So alpha is 4 radians per second squared at 0 seconds, and alpha is 4 radians per second squared at 3 seconds. It's constant. Now, I haven't discussed net torque yet, but net torques are what make things angularly accelerate. A net force is what makes something linearly accelerate, or it can be centripetal, but a net torque is what's going to make something start to spin faster or slow it down. So in this problem, we have a disk that's spinning at 12 radians per second. So that's our initial angular velocity, 12 radians per second. And then it says we have this net torque, and it accelerates it at 6 radians per second squared. So our alpha is 6 radians per second squared. And then it says it rotates 100.5 radians. So that means our theta, our angular displacement, is 100.5 radians. And it says what's its angular velocity after this happens. So we're looking for angular velocity final. So that's going to be omega final squared equals omega initial squared plus 2 alpha delta theta. Because we don't have time in here, so we're going to have to use this formula. So that gives us omega final squared equals 12 squared plus 2 times 6 times 100.5. And when we add these together and take the square root of both sides, we end up with omega final is equal to 36.7 radians per second. In this one, it says we have a wheel rotating in such a way that its angular displacement in a time t is given by theta equals at squared plus bt cubed. A and b are constants. And it says determine the equations for angular speed and angular acceleration. Well, if we have theta equals at squared plus bt cubed, what's the formula for speed? Well, that's going to be d theta dt. That's omega. So what do we have to do? we have to take the first derivative of this. So what's that going to be? That's going to be 2at plus 3bt squared. And it says find a formula for the angular acceleration. Well, that's going to be d omega dt. So we're going to take the derivative of that, and that's going to be 2a plus 6bt. I know this is a lot to do, but stick with it, because once you see a bunch of these done, you can do any of them, and they end up being pretty straightforward. So let's look at another one. It says we have a car accelerating uniformly from rest, and it reaches a speed of 22 meters per second in 9 seconds. And the diameter of the car tire is 58 centimeters. Convert to meters, so that's 0.58 meters. Determine the final angular velocity of a point on the rim of this car tire. So we have our simple formula of converting from linear speed, which in this case is the tangential speed of the tire, and we just do r omega. So that's going to be 22 equals 0.29, and that's going to be times omega. Remember, that's the diameter, so we have to cut that in half. So that gives us 75.9 radians per second. In part B, it says find the angular acceleration of the tire. So for that, we can just do what we've done before, omega initial plus alpha t, and it says it starts at rest, so that becomes 0. So all we have to do is put in the 75.9 we solved for before, equals alpha times the 9 seconds, and alpha comes out to 8.4 radians per second squared. Okay, so part C says calculate the angular displacement. We're looking for theta in this case. So we can do this without time by saying omega squared plus 2 alpha delta theta. And we know this is 75.9 squared is equal to, it started from rest, and we have 2 times the alpha, which we just solved for, which is 8.4, times delta theta, and we get a delta theta of 342.9 radians. What is the final angular velocity in revolutions per second? So this is a little tricky. We know what it is in radians per second, but they're asking us essentially not to calculate something new, but to do a conversion. So we know we have 75.9 radians per second, and 1 revolution is 2 pi radians. So if we multiply through, and we'll be dividing by 2 pi, radians will cancel, and we'll be left with revolutions per second. So that angular velocity in revolutions per second is 12.1 revs per second. Okay, in this one we have a wheel that slows down. So this is a good one because we have a negative alpha in this case. So it's rotating at 10 radians per second. So we can do omega final equals omega initial plus alpha t. And our final is 2 radians per second, and our initial is 10. So that's going to give us a negative answer. We know the time. Time is 6 seconds. And that's going to give us a negative answer of negative 1.33 radians per second squared. In other words, every second that goes by, it slows down by 1.33 radians per second. The next question says, find the tangential acceleration of a point on the wheel that has a radius of 0.2 meters, 0.44, and 0.89. So to be able to find that tangential acceleration, we're going to have to do ralpha. So we're going to have A tangential is equal to 0.2 times negative 1.33. So that's a tangential acceleration of negative 0.27 meters per second squared. And then we just repeat this process. A tangential at 0.44 is 0.44 times negative 1.33, which is going to be negative 0.59 meters per second squared. And then finally, in the third one, we're just going to have 0.89 times negative 1.33, or a tangential acceleration of negative 1.2 meters per second squared. And for the last one here, it says we have a rotating disk that's given a speed of omega equals 4ct squared plus 2t. Give us determine an equation for the angular displacement and angular acceleration. Well, we want to find both of these. Let's do angular displacement first. So we're moving from angular velocity to angular displacement. And what is that going to be? Well, that's going to be the integral of angular velocity. So we're going to do the integral of 4ct squared plus 2t. So do the integral on this, and that's going to be dt. And that is going to come out to 1.33 ct cubed plus t squared. Now, to do the angular acceleration, that's going to be d omega dt, and that's going to be equal to alpha. So we just do the first derivative, and the first derivative of 4ct squared would be 8ct plus 2.